Okay, so we are done with chapter 1. We've done a few sample problems for the problem sets you're going to see. We've dug a little bit into summary 1, and I think we're moving through the text pretty well. So let's just get into chapter 2 now. And I think what we'll see is this first chapter 2 keeps it, there's a lot in here. I mean, there's a lot of fantastic information here, but it really starts out very simply, and it's just solar thermal energy, right? So we spent a little bit of time talking about the 5.4 million exajoules of solar energy that we have access to. The question is, how do we put them to use, right? And I think I also talked about the fact that all cars really are solar cars. Did I mention that last time? Yeah. So, but the point here is that we're gonna take the energy from the sun that's hitting the planet now and make our lives better. So this very first thing, solar panels mounted on the roof. There are several of these in town. Glen Kreisel has some over here at the corner of Thames and Strand. There are several houses like this in the Rattlesnake. Allison Sweeney, who graduated from this program in 2011, was working for Liquid Solar in Bozeman. Solar Plexus puts this type of installation on. The Axeman actually put a bid to do solar thermal on Lomason. There have been various companies to put solar thermal on the roof of the Grizz swimming pool. So this stuff is more prevalent than you might think. Sometimes a little more of a challenge in Montana where you can hit freezing. It's just a matter of putting a heat exchanger in and using a substance like glycol that doesn't freeze at the same temperatures that water does. Number to keep in mind here is what we're looking at is about 1,000 watts per square meter. So a lot of the same numbers that we were doing in terms of how many solar panels would it take to solarize the whole planet. 1,000 watts per square meter on peak. And we're going to see a little bit here in the chapter that 1,000 watts per square meter, if you want to turn that into joules, all right, so if we're looking at solar thermal, how many watts to run a house? Okay, let's back up. How many watts to run a human? Metabolically. 15. Yeah, okay. How many, so one human power. Let's write it differently. One human metabolic power. How many watts to run a human technologically?
Is it like 500?
Yeah. So if you look at it in terms, you can do the power equation and the energy equation the exact same way. We know that a human is 10 megajoules metabolically, 200 megajoules technologically. North American is 1,200 megajoules technologically. So, obviously we don't just live in our houses, but well, we do live in our, obviously all of our energy consumption is not just through our house. Some of it's through our transportation, some of it's services, etc. If we just make the assumption that your house is about half of your energy, well, first let's go to power. So there's a 100 watt person. We're going to multiply that by 120 to get to one human techno power. So 120. So 1, 2, 0, 0, 0 watts. One human techno power, and then we'll go to the house. We'll just assume a house is half of that. 6,000 watts. One human house techno power. This is why these notes will not make sense unless words are coming out of my mouth when I'm writing on the board. So it's 6 kilowatts. 1 house power. And, okay, it's different for every person, but this is just kind of back of the envelope. Now, of those 6 kilowatts, what fraction is heat and what fraction is electricity? You got gas flowing in, you got electricity flowing in both. What's the breakdown between those two?
Yes, a lot more as heat.
There's a lot more juice coming in as heat than electricity in general. Now, it's different if you're where it's warmer. You might have a lot more electricity coming in because you're trying to cool things off rather than heat. But it's about a 5-to-1 ratio. To run a house is about 1 kilowatt to run your house for electric. And that's going to leave us with about 5 kilowatts for heat. Now, I just mentioned that the solar constant is about 1,000 watts per square meter. How big are one of these things are you going to have to put on your house in Montana to heat your house? You might just say off the top of your head, well, 5 square meters, right? Well, if the sun was shining all the time, that would be true. So if you had 100% capacity would yield 5 square meters because you need 5 kilowatts of heat. Well, fact is, sun only shines about 1/6 of the time on average in Montana. So at 1/6, you got to bump that guy up to, 30 meters squared. Start getting into January, February, it's going to get a little bit worse. But I don't know, it's not, 5 meters, 15 feet by 6 meters, that's the size of your roof. So it actually pencils out about right that you could pull this off by covering your roof with this in Montana, on average. And I just mentioned a second ago that if you buy your neighbor's house, fill it with hot water, there's your bank. So it's not outside the question to think that you could potentially do this with the right technology, with the right installation, with the right pipes, et cetera, et cetera. It's not. It's a good ballpark estimate. Okay, so there's your solar thermal. That's the outside. That's what collecting it. What color are those things? Black. Why are they black? Well, so that you get the photon to actually be absorbed rather than reflected or transmitted. You want all those photons to go right into that sucker. Okay, now, there's your black collector. On the inside, and we built a couple of these in the practicum. They're sitting right back out here. They worked so dang well, they made steam and ruptured. It was amazing. So we made some solar thermal. We'd always just done the solar thermal with the air in the past. We made solar thermal with water, and somebody forgot to turn the pump off, and boom! I mean, it exploded. It's pretty amazing. So you can collect solar energy in pipes in the summer in Montana, no problem whatsoever. Okay, right. So the hot water rises. That's why we've got the hot coming out the top. Inside, this is your heat exchanger. I mentioned the fact that if you've got a long cold spell and you've got fluids kicking around up here on the outside, you run the risk not of an explosion from steam, but an explosion from freezing water. So that's why you're going to want to run a fluid that does not freeze at the same temperatures that water does. And you also don't want to mix that fluid with the water that you might shower with, drink with, etc. So that's the reason for the heat exchanger. Temperature sensor says, hey, we got hot up top, cold in here, turn the pump on. Or, hey, we got plenty of heat, we're about to boil, just do your thing. Don't explode. I don't see a pressure relief valve on here, but that'd be a good idea too. Because they can get hot. Okay.
Is that the one they did this summer?
Yeah, actually built three solar thermal with fluid this summer. And the issue we ran into, just because of our limited tubing bending capabilities, we made a spiral instead. Here you can see that these tubes are sort of vertical. Another option is to sort of let them raster back and forth. But the problem with our spiral, the water would sort of go up and then down, then up and then down, then up and down. It got so hot in these tops that it just kept wanting to go up, and there was nowhere to go up, so it went out and ruptured through the tubing. But so there is a little bit of geometry involved here in terms of making the tubing in the right configuration. All right. These are just the three basic components of any solar thermal system. What's the glazing doing for you? Why have the glass on there? What's the importance of that?
It's protecting damage from the rain.
Protects damage. A couple of more subtle things. What's that?
Something about reflection?
Yeah, you're gonna want something that actually has a high emissivity, something that has very very low reflectivity. You really don't want reflection to happen on the top surface. What about the back surface, though? You actually do want reflection to happen on that surface. So it's not only allowing transmission to happen through, but preventing reflection on the back. And as I mentioned before, the longer wavelengths coming off of this guy are actually going to be reflected. And obviously, where they go? Well, hopefully as much as possible into the absorber. That's how you're going to jack up your efficiency. Why do you have the insulation on the back? Well, so you don't get radiation, conduction, and convection off the back. That's keeping the heat in. That's where you want it. Pretty simple. Okay, so here's an example of a solar thermal technology at work in Greece. This is a thermal siphon, and they're actually allowing the pressure differences in the water to do the pumping for them. So the water more or less pumps itself into this top container, and there's enough of a head on this. If you put it on your roof, then you don't actually have to pressurize the water. It's just more or less, if you got a water supply upstream, the thermal siphon effect allows it to pump up into this container, and then you've got some head to take a shower with. We actually built one of these several years ago. Okay, this is what I kind of keep talking about in terms of photons bouncing around. So here's your 5.4 million exajoules of energy coming in from the sun. This funny looking curve, you can see it's got a little curve here. It's got another curve at the top. Then it's got another curve right here. This is actually, believe it or not, a fourth order equation. It's a plot of the Siphon-Boltzmann equation. And it says that energy is proportional to temperature to the fourth power. So if you remember from your math, a parabola has a single bend. If you go to something to the third power, it's got two bends, 1, 2. But once you get to the fourth power, it's got 3 bends in it, and that's what this is. So this is actually an equation that is predicted based on the temperature of whatever star is shining. And so there's really good connection between theory and what we see. Now, what's missing in this little gap here? Well, that's the chunk that was absorbed in that very first figure that we were looking at an hour or so ago. That's the stuff that's absorbed by the atmosphere. What's left over? Well, this is when it hits the surface. This is the part we can see, obviously. There's your 400 to 700 nanometers. What are all these other funny little wiggly lines? Where's that coming from? Why isn't it just flat? So, what's that?
Sun's ray.
Well, no, because you can see what's hitting the top of the atmosphere is smooth, but there are a lot of different molecules in the atmosphere. And just like I said a second ago, go stand outside and see if the sun makes you hot or not. Well, most of that radiation that hits you is absorbed. Some of it passes right through you. Well, there's all kinds of molecules in the atmosphere. This is just a representation of what passes through versus what gets absorbed. And the last thing I want to say before we leave, this is the Earth's radiation profile. You yourself have a radiation profile. Your car engine has a radiation profile. This is the stuff that's bouncing back off the planet, and it's a lot of this that's trapped by the CO2 in the atmosphere. So that's the big kind of the big picture on solar thermal. All right, and then we'll get into some of the instrumentations. We'll look at how much sunlight hits the planet. We'll look at the effect of the Earth's tilt. Look at the effect of the seasons. All kinds of fun things to consider. Oh, here's another really good figure though. Tie this figure with the one I was just looking at because it shows this transmittance. That was that reflection we were talking about in the solar thermal. And so glass can be your friend. I mean, glass is the thing that's sort of allowing the interior of rooms to stay as warm as it is. It's also a similar effect to the greenhouse gas effect. Okay, that's all I want. Thank you, and finish up your bio sketches, please. That'll be your first little grade, if you will, and then we can move on to the summaries and problem sets.